Hello friends, this is Dharmin Patel. Welcome to the lecture series of Mathematics 2. In this lecture, we will discuss the higher order ordinary linear differential equation. In the previous lecture, we discussed the first order, first degree ordinary differential equation and first order higher degree ordinary differential equation. Let us start higher order ordinary linear differential equation. The general form of the higher order ordinary linear differential equation is of the type Fn d raised to n y by dx raised to n plus fn minus 1 d raised to n y by dx raised to n minus 1 up to f2 d square y by dx square plus f1 dy by dx plus f0 y equal to rx. Call it equation number 1. This equation number 1 is nth order linear differential equation because highest order derivative present in differential equation is nth order. Here f1, f2, f3 are some functions of x as well as rx be also function of x. Now to solve this type of differential equation we will take the d by dx equal to d. Here d by dx is a differential operator and we are taking the d for it. Then our equation becomes look like fn d raised to ny plus fn minus 1 d raised to n minus 1 y up to f2 d square y plus f1 dy plus f0 y equal to rx. After taking y common, we get fn d raised to n plus fn minus 1 d raised to n minus 1 up to f2 d square plus f1 d plus f0 into y rx equal to 0. Here we divide this differential equation in two parts. If Rx is 0, then it is known as homogeneous linear differential equation or homogeneous linear ordinary differential equation. Here it is denoted as Fn d raised to n plus Fn minus 1 d raised to n minus 1 up to F2 d2 square plus Fn d plus F0 y equal to 0. And second type is if Rx is not equal to 0, then it is non-homogeneous linear differential equation. To solve non-homogeneous differential equation, we have to use the homogeneous differential equation solution. First of all, we will see the homogeneous linear differential equation and its solution. Let us start with the homogeneous linear differential equation with constant coefficient. So here our differential equation is fn d raised to ny by dx raised to n up to f2 d square y by dx square plus f1 dy by dx plus f0 y equal to 0. Call it equation number 1. Be a homogeneous linear differential equation because Rx is 0. That means right hand side is 0. When our right hand side is 0 in the higher order linear differential equation, then it is homogeneous linear differential equation. Here we are taking f1, f2, fn are constants. Then our differential equation is known as higher order ordinary linear differential equation with constant coefficients. To solve this differential equation, we will take the d by dx equal to d. Then our equation becomes fn d raised to ny plus fn minus 1 d raised to n minus 1 y up to f2 d square y plus f1 dy plus f0 y equal to 0. Now taking y common, we get fn d raised to n plus fn minus 1 d raised to n minus 1 up to f2 d square plus f1 d plus f0 y equal to 0. Here we can't take y equal to 0, so we have to take fn d raised to n plus fn minus 1 d raised to n minus 1 up to f2 d square plus f1 d plus f0 equal to 0. This equation is known as auxiliary equation for our differential equation number 1, and our solution is depends on its factors, and after factorizing it will be look like d minus m1 into d minus m2 into d minus m3 up to d minus mn equal to 0. Here we have n factors because our differential equation order is n. After solving this factor, we get roots of auxiliary equation are m1, m2, mn, and our solution of the differential equation number 1 is also depends on these auxiliary roots. Here we will see the how it is depends on our auxiliary roots. The general solution of higher order ordinary linear differential equation which is depends on auxiliary roots. Here our differential equation is f d raised to n f1 d raised to n minus 1 up to f0 y equal to 0. It is our nth order ordinary linear differential equation with constant coefficient. Auxiliary equation we get fn d raised to n plus fn minus 1 d raised to n minus 1 up to f2 d square plus f1 d equal to 0. And after factorize we get dm minus 1 into dm minus 2 into dm minus n equal to 0. Already we seen in the previous slide, and auxiliary roots are m1, m2, mn, and our solutions is depends on these auxiliary roots. Here d minus m1 is equal to 0, or d minus m2 equal to 0, or d minus m3 equal to 0. These are the first order differential equation. Let us see how to solve them. So here we will see the only one differential equation, d minus m1y equal to 0. That can be rewritten as dy minus m1y equal to 0. dy by dx is the value of d, so we put here dy by dx minus m1y equal to 0. That is dy by dx equal to m1y, which is our first order first degree differential equation, and it can be solved by separable variable method, and that can be rewritten as 1 upon y dy equal to m1 dx. After taking integration both sides, we have a solution y equal to c1 e raised to m1x. It is very easy to solve, and it is coming from separable variable method. Similarly, we can find the other solution as y equal to c2 e raised to m2x for second vector, y equal to c3 m3x for the third factor, up to so on, and y equal to cn e raised to mnx for nth factor. This method is applicable when all auxiliary roots are different. If some auxiliary roots are same or complex, then we cannot easily find this solution. Let us see some examples in this case. d square y by dx square plus 3 dy by dx plus 2y equal to 0 be a second order ordinary linear differential equation, and it is a homogeneous because right hand side is 0. Now it can be rewritten as d square y plus 3dy plus 2y equal to 0, and d is differential operator, and the auxiliary equation coming from it is d square plus 3d plus 2 equal to 0. After factorizing this auxiliary equation, we get d plus 1 and d plus 2 as a factor. And first we solve this factor. First factor is d plus 2y equal to 0. That can be rewritten as dy plus 2y equal to 0. Here dy by dx plus 2y equal to 0 because we have a d value is dy by dx. And dy by dx can be rewritten as minus 2y. It is a first order first degree ordinary differential equation, and it can be solved by separable variable method. Here we can rewrite as 1 upon y dy equal to minus 2 dx. After taking the integration, finally we get the solution y equal to c1 e raised to minus 2x, and here c1 is an arbitrary constant. Similarly, we can find the second solution, which is y equal to c2 e raised to minus x. Here C1 and C2 are arbitrary constant. Here we found the solution from the separable variable method after converting second order into the first order. But we have to check, is it a solution of our original differential equation? So now we verify y equal to c1 e raised to minus 2x and y equal to c2 e raised to minus x are solution of our differential equation y double dash plus 3y dash plus 2y equal to 0. Here we have a first order differential equation d plus 2y equal to 0 and d plus 1y equal to 0. First of all, find the y dash from our y equal to c1 e raised to minus 2x, which is y dash equal to minus 2 times c1 e raised to minus 2x. Then y double dash is 4 times c1 e raised to minus 2x. Now we will put in our differential equation y double dash plus 3y dash plus 2y equal to 0. Then after putting this values y dash and y double dash in LHS side of our differential equation, we get the 0. Then therefore our first solution c1 e raised to minus 2x be a solution of our all differential equation, as well as second solution is c2 e raised to minus x and y dash is minus c2 e raised to minus x. Y double dash is c2 e raised to minus x. Now we will put in y double dash plus 3y dash plus 2y equal to 0, then we get the RHS is 0 after putting the e raised to minus x in LHS side. Therefore, both are solution of our original differential equation d square y by dx square plus 3 dy by dx plus 2y equal to 0. Let us see our second example. D square y by dx square minus 5 dy by dx plus 6y equal to 0, or it can be rewritten as y double dash minus 5y dash plus 6y equal to 0, and it can be rewritten as d square minus 5d plus 6y equal to 0, and its auxiliary equation is d square minus 5d plus 6y equal to 0. Here d is our differential operator d by dx. After factorize these equations, we get d minus 2 and d minus 3 as a factor. Now we have a two first order differential equation, d minus 2y equal to 0 and d minus 3y equal to 0. After solving first differential equation, we get the first solution y equal to e raised to 2x, and we put in our differential equation y double dash minus 5y dash plus 6y equal to 0 to verify is it the solution of our original differential equation or not. So first of all, we find y dash 2 e raised to 2x, y double dash is 4 e raised to 2x. Now we will put y dash, y double dash in LHS side, then we put y double dash equal to 4 e raised to 2x, y dash equal to 2 e raised to 2x, and y equal to e raised to 2x. Then finally we get 10 e raised to 2x minus 10 e raised to 2x, then it is 0. Therefore, y equal to e raised to 2x be a solution of our second order differential equation. Similarly, from d minus 3y equal to 0, we have a solution by separable variable method, which is y equal to e raised to 3x, and y dash is 3 e raised to 3x, y double dash is 9 e raised to 3x, and put in the LHS side of the differential equation y double dash minus 5y dash plus 6y equal to 0. We get 15 e raised to 3x minus 15 e raised to 3x, and that will be 0. So second one is also solution of our original differential equation. But here y equal to e raised to 2x and y equal to e raised to 3x are particular solution of our second order ordinary differential equation. We want to find the general solution. So let us see how to find the general solution of our differential equation y double dash minus 5y dash plus 6y equal to 0. As y equal to e raised to 2x and y equal to e raised to 3x are solution of our differential equation, we have a y equal to c1 e raised to 2x plus c2 e raised to 3x be also solution of our differential equation number 1, where c1 and c2 are arbitrary constant. First of all, y equal to c1 e raised to 2x plus c2 e raised to 3x, y dash equal to 2 c1 e raised to 2x and 3 c2 e raised to 3x, y double dash becomes 4 e c1 e raised to 2x and 9 c2 e raised to 3x. Now we will put y dash and y double dash in our differential equation number 1, which is y double dash minus 5y dash plus 6y equal to 0. And after putting this value in our differential equation LHS side, y double dash minus 5y dash plus 6y, then we get finally 10 c1 e raised to 2x minus 10 c1 e raised to 2x plus 15 c2 e raised to 3x minus 15 c2 e raised to 3x, that means equal to 0. That means we have a c1 e raised to 2x plus c2 e raised to 3x be a general solution of higher order ordinary differential equation y double dash minus 5y dash plus 6y equal to 0. This is the general solution of our differential equation y double dash minus 5y dash plus 6y equal to 0, and it is also known as complementary function, and it is denoted as yc. Let us see the steps to find the general solution of higher order ordinary linear differential equation in homogeneous case. This is our nth order ordinary linear differential equation in homogeneous case, and its auxiliary equation is d raised to n plus fn d raised to n minus 1 plus f2 d square plus f1 d equal to 0. And After factorize the auxiliary equation, we get d minus m1, d minus m2, d minus mn are 0. Therefore, m1, m2, m3 up to mn are solutions of auxiliary equation, and these are the auxiliary roots. Now our particular solutions are depends on these auxiliary equations, and from them there are n linearly independent functions y1, y2, yn of x which satisfies our differential equation, and these are the particular solutions of our differential equation number 2, and the general solution of our differential equation becomes y equal to c1y1 plus c2y2 plus cnyn, where c1, c2, cn are arbitrary constants. So this is the steps to find the general solution for the higher order homogeneous linear differential equation. In the next lecture, we will see the solutions types for higher order homogeneous linear differential equation. Thank you very much for watching.